What if I told you that there exist regions in space where gravity is so strong, nothing can escape it, not even light? Imagine, if you will, a celestial body, a region in the fabric of space that's so dense, so heavy that it pulls everything into it. This, my friends, is the enigma we call a black hole. Now, black holes aren't vacuums, sucking up everything in their path, as some might think. No, they're more like cosmic anomalies, areas in space where gravity has gone wild. They possess such an intense gravitational pull that anything straying too near spirals inward, lost forever, even the very light that illuminates our universe. These mysterious entities, these black holes, are a testament to the strange and wondrous complexities that exist out there in the vastness of space. So how did we come to know about these mysterious entities? Let's delve into the history. The concept of dark stars that trap light dates back to the 1780s, but the real game changer was Einstein's general theory of relativity. Let's journey back to the late 18th century. A curious Englishman named John Michell proposed the idea of dark stars. According to Michell, these celestial bodies were so massive and gravitationally powerful that not even light could escape their pull. This was a radical idea, but it was largely forgotten for more than 100 years. Fast forward to the early 20th century. Enter Albert Einstein, the man who would revolutionize our understanding of the universe. In 1915, Einstein presented his general theory of relativity, a theory that reimagined gravity not as a force, but as a warping of space-time by mass and energy. This was groundbreaking as it shifted the paradigm of physics and set the stage for the modern concept of black holes. Einstein's theory suggested that if an object was sufficiently dense and compact, it could deform space-time to such an extent that it would form a sinkhole from which nothing could escape, not even light. This was the birth of the concept of a black hole as we know it today. However, Einstein himself was skeptical. He thought that nature would prevent such extreme space-time deformations. Despite his doubts, his theory stood firm, and it wasn't long before other scientists began to explore the implications of his revolutionary ideas. The 1930s saw a flurry of activity. Theoretical physicists such as Oppenheimer and Snyder used Einstein's equations to predict the existence of black holes. They suggested that a massive enough star, once exhausted of fuel, could collapse under its own gravity to form a black hole. So the stage was set. The theoretical foundation for black holes had been laid, and the scientific community was abuzz with the possibilities. The concept of a dark star had evolved into something far more mysterious and intriguing. Einstein's theory paved the way for the next significant contribution, one that came from a young Indian astrophysicist. Subrahmanyan Chandrasekhar, a young Indian astrophysicist, proposed an idea that was initially met with skepticism. Picture this. It's the early 20th century, and Chandrasekhar is sailing from India to England. The sea's vastness and the sky's expanse make him ponder on the fate of massive stars. His calculations led him to a startling conclusion. Stars of a certain mass, approximately 1.5 times the mass of our Sun, would not end up as white dwarfs as previously thought. Instead, they would continue to collapse under their own gravity, shrinking indefinitely, creating what we now call a black hole. This idea was so revolutionary, so contrary to accepted ideas of the time, that it was met with skepticism, even derision. The most vocal critic was the renowned astrophysicist Sir Arthur Eddington, who dismissed Chandrasekhar's theory as mere mathematical game-playing, an aberration of the laws of physics. But Chandrasekhar stood by his findings, even in the face of such formidable opposition. He was eventually vindicated. His theoretical limit, now known as the Chandrasekhar limit, has become a cornerstone of astrophysics. It's a fundamental factor in determining the life cycle of stars and the formation of black holes. When a star of sufficient mass exhausts its nuclear fuel, it explodes in a supernova. If the remaining core is less than the Chandrasekhar limit, it becomes a neutron star. But if it's more, no known force can resist the gravitational pull. The core collapses to a point of infinite density, a black hole. Chandrasekhar's work was not just an academic exercise. It revealed a new facet of our universe, a darker, more mysterious side. It laid the groundwork for our understanding of black holes, these strange celestial entities that warp space and time around them. Chandrasekhar's work was a stepping stone, but it was a man named Stephen Hawking who brought black holes into the limelight. Stephen Hawking, a name synonymous with black holes, revolutionized our understanding of these celestial bodies. Stephen Hawking, an extraordinary mind of the 20th century, brought a seismic shift in our comprehension of black holes. Being diagnosed with a debilitating motor neuron disease didn't deter him from his pursuit of the mysteries of the universe. His indomitable spirit led him to make groundbreaking contributions that fundamentally challenged our perceptions of black holes. Hawking proposed that black holes aren't the all-consuming monsters we once thought they were. Instead, he suggested that they emit radiation, a phenomenon we now call Hawking radiation. This was a radical departure from the prevailing belief that nothing, not even light, could escape a black hole's gravitational pull. Hawking's work was rooted in the principles of quantum mechanics and general relativity, two pillars of modern physics that often seem at odds with each other. He proposed that pairs of particles and antiparticles spontaneously pop in and out of existence near the event horizon of a black hole. One of these particles can fall into the black hole, allowing the other to escape as Hawking radiation. This theoretical discovery was monumental. It suggested that black holes could shrink and eventually evaporate over time, a concept that contradicted the traditional view of black holes as permanent, unchanging features of the cosmos. Hawking's proposal of black hole evaporation also raised profound questions about the nature of the universe and our understanding of reality. It led to the information paradox, a contentious issue that still sparks heated debates among physicists today. The paradox questions whether information about the physical state of particles entering a black hole is permanently lost when the black hole evaporates, a notion that challenges the fundamental principles of quantum mechanics. Hawking's contributions to the study of black holes have left an enduring legacy. His theories continue to shape the way we perceive these enigmatic celestial bodies and inspire ongoing research to reconcile the paradoxes his work unveiled. From theoretical physics to observational astronomy, the study of black holes took a giant leap forward with the advent of X-ray telescopes. The ability to observe something that swallows light seems paradoxical, doesn't it? Yet advancements in technology made it possible. So let's dive into how we've been able to cast our gaze upon these cosmic mysteries, these black holes. In the latter part of the 20th century, X-ray telescopes played a significant role. You see, while black holes may be invisible to the naked eye, they're not entirely hidden. When matter spirals into a black hole, it heats up and emits X-rays before disappearing forever. These signals, invisible to us but detectable by X-ray telescopes, became our first indirect observations of black holes. As technology advanced, so did our means of observing black holes. Enter the Event Horizon Telescope, or EHT, a global network of radio telescopes. The goal? To directly image the shadow of a black hole's event horizon, the point of no return. A Herculean task, no doubt, yet one that was ultimately successful. In 2019, the world held its breath as the EHT team unveiled the first ever image of a black hole. The image was blurry, like a smoky ring of orange and yellow, but what it represented was crystal clear. For the first time, we were seeing the unseeable, observing the invisible. This was the supermassive black hole at the heart of the Messier 87 galaxy, over 55 million light-years away. That image, that moment, marked a significant milestone in our understanding of black holes. It was a testament to human curiosity and ingenuity, a triumph of theoretical predictions meeting observational confirmation. But don't be fooled into thinking we've solved the enigma of black holes. Far from it. Each observation, each discovery, only deepens the mystery and widens our appreciation of these cosmic behemoths. These observations have brought us closer to understanding black holes, yet they continue to challenge our understanding of physics. As we peer into the cosmic abyss, the abyss also peers into us, reminding us of the boundless wonders that lie beyond our current grasp. Black holes, the universe's ultimate enigma, continue to perplex us, challenging the very laws of physics we hold dear. These cosmic conundrums stand as titanic testaments to the universe's ability to bewilder and astonish. They stretch our comprehension of reality, pushing against the boundaries of what we thought possible. In our quest to decipher these celestial mysteries, we're delving into uncharted territories of knowledge. We're probing the very fabric of space-time, seeking answers in the most extreme environments imaginable. From the earliest theoretical foundations to the latest observational advancements, the journey has been nothing short of awe-inspiring. Yet despite our progress, black holes remain shrouded in mystery. They're the universe's ultimate riddle, a riddle we're yet to fully solve. The enigma persists, but so does our curiosity, our tenacity, our relentless pursuit of understanding. As we continue on this journey of discovery, one thing is certain. Black holes will always captivate us, inviting us to peer deeper into the mysteries of the universe.